Good morning, friends. Myself Shankar Bhanuse. Today we are going to see one of the important bit of complex variable, that is harmonic function. In previous video we have seen for the given analytic function how to find a real part and imaginary part, that is u and v. Okay. In today's lecture we are going to discuss harmonic function. What is meant by harmonic function and how to find the harmonic conjugate of the given function f of z. Okay, first let us start with the definition of harmonic function. If u is equal to f of xy is said to be a harmonic function if del square of u is equal to 0. Del square is a second order differential operator. If you operate on u, that is we will get u double x plus u double y is equal to 0. Then we can say that u is a harmonic function. Also, the del square u is called a Laplace equation. A function which satisfies this Laplace equation is called harmonic function. This is definition. Now let's go for the examples. Suppose example number 1. Common question I have considered here. Show that the following functions are harmonic and find the analytic function f of z and their harmonic conjugate and their harmonic conjugates. Let us start the first one. Consider u is equal to sin hx cos y. Let u is equal to sin hx cos y. Ux is equal to cos hx cos y. The partial derivative of u with respect to x, treating y as a constant, means we have to keep cos y as it is. Sin hx derivative is cos hx. Similarly, differentiate again with respect to x. Again cos y as it is, derivative of cos hx, it is sin hx. Okay. Similar way, try to find uy. That is, at the time sin hx will be as it is, and the derivative of cos y is minus sin y, and u double y similarly minus sin hx cos y. If you observe, u double x and u double y both are in opposite sign. U double x is positive and u double y is negative, and all terms are same. That means addition of these two, u double x plus u double y, is equal to 0. As it is so, then we can say that the given function u is a harmonic function. To find f of z, let the second part, this is our first part of the example, that is we have shown the u function is harmonic. Let's go for the second part. To find f of z, let u is equal to sin hx cos y. As the real part is given for the complex function f of z, we know that by Milne-Thomson method the formula f of z is equal to integration of phi1 z0 dz minus I phi2 z0 dz, where phi1 of z0 is equal to ux and phi2 of z0 is equal to uy. Okay, give it equation number 1. Let's start. First find out phi1 and phi2. For that we need ux. Already we have found ux at the time, at the starting of the example. The ux is equal to cos hx cos y. Phi1 of z0 means in the place of x we have to put a z, and in the place of y we have to put 0. After simplifying we get phi1 of z0 is equal to cos hz. Okay, and uy is equal to cos hx sin y. After putting these values we'll get value 0, because sin y is 0 and cos y is 1. Therefore phi1 is cos hz, that is cos hyperbolic z, and phi2 z0 is 0. Now put all these values in equation 1, so that equation 1 becomes f of z is equal to integration cos hyperbolic z dz minus I integration of 0 dz. F of z is equal to cos hyperbolic z dz. F of z is equal to integration of cos hyperbolic functions derivative of cos hz and integration both are positive, so that integration will be sin hz plus c, sin hyperbolic z plus c. This is equation 2. This is second part of the example we have completed. Go for the third part. Find its harmonic conjugate v. Okay, put z is equal to x plus iy in equation second. Suppose in second, if you put z is equal to x plus iy, we get f of z is equal to sin h x plus iy. We know the formula of sin hyperbolic a plus b. It is sin hyperbolic a into sin hyperbolic b plus a, sin hyperbolic a into cos hyperbolic b plus cos hyperbolic A into sin hyperbolic B. Now in this way, if you simplify, we get sin hx cos hiy plus cos hx sin hiy, sin hx cos y plus I cos hx sin iy. Relation between circular and hyperbolic function, if you use, we will get the value of cos hyperbolic hiy is equal to cos y, and sin hyperbolic iy is equal to sin y. As we compare with u plus iv, we will get v is equal to cos hx sin y. The harmonic conjugate of u, is cos hx sin y. Okay, this is the first example. Step 1, show that the function is harmonic. Step 2, find f of z. Third step, to get conjugate, put z is equal to x plus iy. This way you can complete the example. Okay, let's consider now second example. U is equal to y cube minus 3x square y. Okay, u is equal to y cube minus 3x square y. Ux is equal to minus 3 2xy derivative, because derivative of y cube is 0, as we are differentiating with respect to x. Next time, derivative of x will be 1, and minus 3 into 2 6y. U double x is equal to minus 6y. Uy is equal to 3y square minus 3x square, and u double y is equal to 6y. Again, if we add, we will get u double x plus u double y is equal to 0. Implies our conclusion, u is an harmonic function, as it satisfies the Laplace equation. Now to find f of z, let's consider u is equal to y cube minus 3x square y. Again, as the real part is given, we know the result. By Milne-Thomson method, f of z is equal to phi 1 z0 dz minus I phi 2 z0 dz, where phi 1 of z0 is equal to ux and phi 2 of z0 is equal to uy. Ux and uy already we have found, so in that ux and uy put x is equal to z and y is equal to 0, so that we obtain phi 1 of z0 is equal to 0 and phi 2 of z0 is equal to minus 3z square. Okay, first value becomes 0. Now put these values in equation 1, so that f of z is equal to, we get integral 0 dz, phi 1 is 0 minus I integration of phi 2, that is minus 3z square dz. As minus 3 is a constant, take outside, already minus sign is there, therefore minus minus plus becomes plus, 3i remains, integration of z square dz. And we know the integration of z square is z raised to n plus 1 upon z raised to n plus 1, where n is equal to 2, that is z cube upon 3. So that 3 get cancelled, I z cube plus c. Now find its harmonic conjugate, and that is v. For that, what is our step? That is, we have to put z is equal to x plus iy in equation number 2. Just to neglect the integration constant c at that time. Now put I z cube is equal to I, value of z is x plus iy bracket cube. We know the bracket expansion of a plus b. A plus b is equal to a cube plus b cube plus 3b a square b plus 3b square a. In this way, you can expand x cube plus iy cube plus 3x square iy plus 3x I y, the whole term square. Now separate the brackets, that is x cube plus 3i cube. Next, in the last term, I square y square. Multiply I to the bracket, so that it becomes ix cube plus I raised to 4y cube plus 3x square I square y plus 3x I cube y square. Because already I square is there, if you multiply I, it becomes I cube. Increase the power of I by 1, because we are multiplying I to the whole bracket. After that, we know the values. I raised to 4 is nothing but 1, I cube is minus I, and I square is equal to minus I. Put all these values, so that equation becomes ix cube plus y cube minus 3x square y minus 3x I y square. Okay. Therefore, separate the real and imaginary part, construct the part which contains I and which does not contain I, so that we will get f of z is equal to y cube minus 3x square y plus I x cube minus 3x y square. Comparing with our definition, you get v is equal to x cube minus 3x y square. Simple. Okay. Now first two examples we have considered with the real part is given, that is u. Let's consider third example with the imaginary part. Suppose v is given, v is equal to sin hx sin y. Let v is equal to sin hx sin y given function. Differentiate with respect to x, that is vx cos hx derivative sin. We know that it is cos hx sin y, that is cos hx derivative sin hx sin y. This is v double x. Now vy sin hx as it is derivative sin y, it is cos y, and derivative of cos y is again minus sin y, so it is minus sin hx sin y. That is v or double y. I have written there. Therefore, after adding these two, v double x plus v double y is equal to 0. Therefore, v is a harmonic function. Okay, as it satisfies the Laplace equation. V double x plus v double y, like u double x plus u double y. Okay. Second part of the problem, to find the analytic function f of z. Let v is equal to sin hx sin y. We know that by Milne-Thomson method, f of z is equal to integration psi1 z0 dz plus I psi2 z0 dz. Now in the formula we have just made a simple change, that is instead of phi we have used psi, because for v we have to use psi notation, and for u we have to use phi in the formula. Why? Because there is a little bit difference in the formula. Now for psi1 of z0 nothing but vy, and psi2 of z0 is equal to vx. That is a change, that's why we have to use psi. In u, psi1 of z0 is ux, but here vy first term and second is phi2, and middle sign is plus, as comparable to real part formula. Okay, therefore find the values vx cos hx sin y, put value phi2 of z0, psi2 of z0 as vx is there, put there sin 0 0, therefore psi2 will be 0. Go for psi1, psi1 is equal to sin hz. Equation 1 becomes psi1 of z0 dz I psi2 of z0 dz. Integration of psi1 of z sin hyperbolic z is cos hyperbolic z. We know already, we have discussed. Integration of sin hyperbolic or derivative of sin hyperbolic, all are positive. Now let's try to find out its conjugate. Now in previous example u is given, therefore its conjugate will be v. Now v is given, therefore its conjugate will be u, the real part of the complex function f of z. Our usual step, that is z is equal to x plus iy, put f of z is equal to cos h x plus iy. Use the formula of cos hyperbolic a plus b. Remember, cos hyperbolic a plus b is cos hyperbolic a cos hyperbolic b plus sin hyperbolic a sin hyperbolic b. Okay, f of z is equal to cos hyperbolic x, cos hyperbolic iy is nothing but cos y only, plus I sin hx as it is, sin hyperbolic iy is nothing but I sin y, by the relation of circular and hyperbolic function. Now comparing with our u plus iv, we will get the real part of the complex function f of z, that is the conjugate of v is cos hx cos y. In this way we have seen three examples, two examples of real part and one example of imaginary part v. Simple, three steps are there, that is first one, show that it is harmonic. Second, find f of z. Third step, find its conjugate with the substitution x plus iy. Separate the real and imaginary part, construct I and u and v, and write down its conjugate. Okay, similar way you can solve. I have given some example here as a test. You can consider three examples of the real part u and three examples of v. Okay, try it. Thank you. Hope that you have understood. Thank you very much.